All right, so I'm pre-recording this because I know that I cannot participate in live stream after 10 o'clock because I got a meeting at 10. So what I'll do is I'm pre-recording basically the end of the lecture. So I have to do some, time skipping, just to so that I can get to the end of today's lecture. And the first thing I want to do is to kind of give you guys an idea of how to prepare for the exam. I already talked about this quite a few times, but I think doing it in a slightly different way may be helpful. So the first thing I want to do is to illustrate how the processor design is actually very important in this particular exam. So you can print this out on a piece of paper and then use a highlighter to highlight the important components. Now, when I say important, obviously all components are important. In other words, if I just remove one of these tunnels or remove one of these smaller gates, the whole thing is not going to work, not 100%. But when I said important, it has to do with what you do or how you analyze how a slice of ROM or how a microcode slice is going to change or influence the behavior of the processor. So from that perspective, we got a few, all the quote unquote active components are the ones that are important. Active components typically refer to things that can remember a state. So the first one, that can remember a state is RAM. Okay, that's one. And then obviously all the registers are the same, or would fall into this category. So all the registers would include the flags register, the 4 registers inside the register bank, the program counter, the instruction register, and last, obviously not least, the microcode pointer. So you have to kind of keep a list of these items because these items together is going to store the state of the processor. Okay, and what I mean by that is um, um, things can change. Okay, these are the items that can quote unquote change and remember the change. Now everything else can change as well, but they are transient. I'll give you an example of a multiplexer. Okay, so multiplexers are helping or helper components. They're just as important. They're links within a chain to get something done, but they are by themselves. They don't really quote unquote remember anything. So for a multiplexer, um, the select input or the select port is the one thing that influences how it functions. So a multiplexer relies on the select in order to pick one of its inputs to connect to the outputs. That's about it. Some multiplexers has an enable pin, okay, so one extra pin at the bottom or sometimes at the top. That simply means sometimes none of the output may connect to the output. Okay, demultiplexers like this one is exactly the opposite. It has one input, multiple outputs. This one has got an enable pin, so it is possible for the input not to connect to any one of the outputs, and the output is not driven or not specified. The select is the one that selects which output connects to the input. Okay. We have the a few gates sprinkled around the processor. So here's an OR gate, here's an AND gate with a negated input over here. We got adders. We got at least 2. Okay, we got exactly 2. Here's one adder to auto increment the program counter, and here's another adder to auto increment the microcode pointer. We got a few splitters. Okay, we got this splitter to split the output of the ROM, and then this one to split one of the ends of the other splitter. Okay, so that's the kind of important part. We got this splitter to put the opcode into the microcode pointer. So we got just some major components that we need to remember, or but the analysis of the processor start with the components that can remember, which I just mentioned earlier. And then with each one, the first question is it enabled? Because if it is not enabled, If it's not enabled, doesn't mean that it is not important in the operation. But it does mean that it is not going to update. So if it's not going to get updated, then we go like, okay, we'll figure out how it's going to be used, maybe in some other place. But with RAM, if it is not selected, if RAM cell is a 0, that means the D port is not going to be usable in any way, and the A port does not change the behavior of the RAM in any way. So if RAM cell is a 0, that means you can take RAM out of the whole thing, because it's not going to do a single thing. But if RAM cell is a 1, then we have to first find out, is it a read or write operation, and that's by analyzing the load pin or the load port. And then the next two questions, okay, no matter whether it's a read or the write operation, the next two questions is how is the A port connected. If it's a read operation, somebody has to say which page do we turn to. So there are basically only two things that can influence the A port. One is the program counter, and the other one is one of the registers inside the register bank. Now, which one do we choose? Okay, there are four registers in the register bank, and then there's the program counter. But which one is going to specify the A port? Well, that's all done by a bunch of demultiplexers and multiplexers. Okay, so that is up to you to kind of figure out. And then the third question related to RAM is who connects to the data port? If we are reading, then the data port is driven by RAM. So somebody else is getting updated because of RAM. So you should look for a register that has the enable pin being a 1. On the other hand, if RAM is being written to, then we are looking for something that outputs something, okay, such as the Q port of a register. So we have to find out, the Q port of which register is connected to the data port of RAM when we are writing to RAM. So this is the kind of analysis, that you can perform, by looking at specific bits, or in the reverse direction. If you know what operation you need to do, then you look at all of these components and you decide, okay, I think I need RAM to be in write mode, okay, and then you specify, oh, I need register B to specify the A port, and I need register C to receive whatever, to specify the D port, to connect to the D port. And then you just kind of go through the whole thing, find out exactly what components you need to configure and how to configure those components to answer that question. All right, so there's one. Another thing that you might want to do to prepare for the exam, and obviously that is up to you to decide whether you want to do that or not, is to reconstruct some of the memory devices. So I did talk about it, okay, I constructed maybe one or two of those devices. So what you can do is to go back here, and for everything that has a description of how to construct it, go ahead and construct it, okay, in Logisim. And same thing for D flip-flop, a basic level sensitive D flip-flop. Same thing for edge sensitive D flip-flop. I think I created a edge sensitive D flip-flop, so that's done in class. And obviously the analysis is actually important as well, okay, because that is how we understand how the edge sensitive D flip-flop in this case works. So with this one, I do not think I created an actual design, so you can do it, okay. So go ahead and design, go ahead and copy the design in Logisim, and then just exercise it, okay. Have enable being off, and then specify a particular data bit, and then clock it and see whether it remembers the state. Okay, it really should not, right? So next, turn enable back on, specify one particular bit, and then turn enable on, specify a particular data bit, and then have a positive edge at the clock pin, and you should see that the output of SRC changing. I might actually have done this one too, because I remember the name of that SR latch. Yeah, so I think I did this one too. I think I also demonstrated how this one works. The next one is a very slight modification, if I may say that, of the earlier one. All it does is to add the reset capability. And once you have this as one single circuit, then you can create this one over here as a multi-bit register. So that's about it. Um, but you do want to kind of, I think it's helpful to create these circuitry so that you can actually understand and exercise the circuitry to improve your understanding of how it works. Okay, so that's I think that's highly recommended. Um, and then with floating point numbers, you probably want to be able to finish the entire conversion. Our homework assignment did the conversion up to a certain point, which is basically having a normalized mantissa that occupies exactly 64 bits, um, and a exponent of 2 to help compensate for that kind of gigantic mantissa. So to convert that into an actual double is not really too many steps. Okay, you have to shift the sign bit in, and then you have to move the binary point from to the right hand side of bit 0 to the right hand side of bit 63. So that would take 63 shifts, right? And then those 63 shifts will influence the exponent of 2 in a particular way. And then once you know the finalized exponent of 2, you have to add 1023 to it to become the biased exponent. And then that needs to become bit 52 to bit 62. And then the fractional part of the mantissa, not counting the 1 point, okay, the rest of it becomes bit 0 to bit 51. So from that point on, it's actually relatively easy to do the rest of the conversion. So my recommendation is, if you have time, go ahead and perform that portion too, um, so that you can basically finish the entire process. Okay, so I think that covers most of the content regarding the exam. So now we can move on to the lab. All right, so the lab is about push and pop operations, which is what we need in order to implement subroutines. So the first thing I need to do is to show you what the passcode is. So the passcode is just LIFO, last in, first out. Okay, and so what we'll do at this point is to look into the lab just a little bit. Okay, so we'll look into the questions a little bit. And these questions reflect here what we did in class already. Um, hmm, that is not what I want to show. All right, we'll update the question. All right, there we go. So these questions relate to what we talked about today, and it's really just trying to relate the instructions, the mnemonics of instructions to your operations on the stack. So you have to first remember, what operations on the stack we talked about in class, in our examples, and probably in class I have already talked about the specific instructions already. So you just have to kind of go back and figure out which instruction accomplishes a particular stack related operation. And to do today's lab, you can use the simulator to help you. So between the assembler and the simulator, that should make today's lab, actually somewhat, easy. Okay. The last one is a little bit more difficult if you were to do it without using the simulator. This one asks how many bytes are used on the stack during the following program that calls a recursive subroutine. So, in other words, it is asking at one point in time during the execution of this program, it would use up a certain number, of stack space. So it's basically asking during the entire execution of this program, okay, how low, well, okay, that's already giving you an answer, okay. It's asking you how many bytes on the stack were being used at the same time, were in use, I should say, were in use at the same time, okay. um, in class, we'll talk about how the stack is basically has two portions. One portion is in use, and the other portion is not in use. Okay, so you have to relate that discussion to answer this question. Okay, this question is best answered using the command line, the CLI method of running a program, which also basically it says you have to remember. So I'm gonna change the question here because I want to make sure whatever you do in this particular question, it's gonna work in the CLI. So I'm just putting a no op at the very beginning, which is what you need in order for a program to work in assembly. So update the question. There we go. So this no op is quite important. So if I don't remember to say that, you kind of have to remember that a no op is needed in order to start the execution of a program in CLI mode in Logisim. Okay. So with this particular question, using the trace analyzer is very helpful because basically what you really need to do is to track down one particular register and find out what is the extent of change to that register. Okay, I'll put it that way because I don't want to give away the solution too much. So you want to find out the extent of changes to that particular register, and without the trace analyzer, it's very tedious to do. With a trace analyzer, you just kind of look at one particular column, in the result of the analysis, and then just kind of scan and look for changes to a particular register, and figure out, oh, okay, this is as far as this register went when the program executed, and from that, don't just write down that number because that is not the answer. Okay, so from that value, then you can deduce, what the answer of the question is. So that's today's lab. So I think I have recorded enough for from 10 to basically 10:20. Let me just double check. I'm looking at the status of Logisim, and interestingly, it doesn't seem to tell me how long the recording has been. I can see the clock, but the clock itself doesn't really tell me anything because I forgot to remember when I started, so which is kind of important. So what I'll do is I'm doing something off screen, to answer my own question. So just give me a second. And today is the 15th. There we go. Nope, that one did not help either. Okay, but I think I got enough time, to cover the 20 minutes that I'll be missing at the end of this lecture. All right.